Hi all. This session is on the overview of multivariate data analysis strategies. And if we are wondering what's so special about multivariate data analysis or what's so significant about multivariate data analysis, to look at a very mundane example, we all enjoy the flavor of good food only if we can see it, we can smell it, and we also are able to taste it. So, the sense of seeing, smelling, and the sense of tasting the food give the complete enjoyment of tasting a food with good flavor. Now, this is a clear indication that even if one of these senses are not working, for example, if we have a stuffy nose or we have a bit of a fever and your senses are not in full form, then the flavor of food is not really enjoyable, or we miss out on any one dimension of the flavor of the food. This is typically the essence of why we don't leave out any variables or we don't leave out any factors during our study. In a typical scenario, let us say if we are looking at the efficiency of a car, the fuel efficiency of a car that we need to analyze, we can say that the engine capacity influences the fuel efficiency of the car. We can also say that the unladen weight of the car influences the fuel efficiency of the car. Both of these are directly related to the potential of the car or the capability of the car. We also have variables such as driving conditions in different traffic scenarios. We have the different times of the day where the traffic could be heavier, and these could also be influences of fuel efficiency of a car. So, we have intrinsic factors that are directly the car's own attributes, and we have the extrinsic factors, the environmental factors. So, for computing the fuel efficiency in a real time scenario, we can't ignore a part of this and take the rest of it. So, this is how multivariate analysis gained importance. In a typical scenario, it is analyzing all the variables simultaneously, not ignoring the effects of one or two of them. And we may perform multivariate analysis with multiple variables in a single relationship, or we could examine them in multiple relationships. Some of the preconditions that we have are all the variables are random in nature and they are interrelated and they cannot be interpreted in isolation. Now, we have been speaking of this term called variables, and variables and factors are sometimes used interchangeably in this session and in other sessions too. Now, a variable is something that helps us in one attribute of identifying a characteristic of anything that we are studying. For example, fuel efficiency of the car was a variable, engine capacity is a variable, and color of a car could be an attribute. Now, I say color of a car is an attribute because it is not measurable, but it is subjective. Whatever is measurable are generally termed as variables, but sometimes even subjective measurements are called variables in some analysis. In this term of multivariate analysis, we have a term called variate, which is quite different from the term variable that I have been using. Now, a variate consists of a set of variables in a linear relationship, and each variable has an associated weight that is empirically determined. Since a variate consists of a set of variables in a linear relationship, a typical example would be the one in the regression equation. The dependent variable y is defined by a set of variables x1 till xn, and the empirical weights which you could probably compute are the ones that are the coefficients associated with each of these independent variables. So, we could determine that y, the dependent variable, is cumulative computation of all the independent variables x1 till xn, which is associated with weights b1 till bn for each of the variables of x1 till xn. So, we could simply say that a variate is a simple result which is a unitary value that represents a combination of the entire set of variables, the entire set of the independent variables in the example I spoke of, chosen to define the objective of the analysis. Now, we must also understand that the statistical techniques that we use is a lot dependent on the nature of our own research problem or the question that we have framed for our research, and also on the nature of our data set. The research questions to solve the research gap or the problem may be related to identifying the degree of relationships among the variables, or it could be for checking for the significance of group differences, or it could be for predicting of group memberships or structure, or it could be time related like the one we use in time series forecasting models. And in order to identify associations between two or more variables, depending on whether their nature of being parametric or non-parametric, correlation and regression or chi-square techniques may be adopted. This can also be done as a bivariate correlation and regression, multiple correlation and regression, canonical correlation, multiple discriminant analysis and Logit regression. Out of these, bivariate correlation is not strictly a multivariate techniques, but provides a good starting point. And typically, multivariate techniques are classified into two groups, the dependence techniques and the interdependence techniques. Now, we first look at the dependence techniques. We have 6 of them. The first one is multiple regression and multiple correlation. Next is multiple discriminant analysis, or the MDA, and the logistic regression. Then the third one is the canonical correlation analysis. The fourth is the multivariate analysis of variance and covariance, which we also call as a MANOVA and MANCOVA. And the fifth one is a conjoint analysis. The sixth is a structural equation modeling and the confirmatory factor analysis. Now, these are not the exhaustive list of the dependence techniques, but they are the most popularly used dependence techniques. We will come back to the interdependence techniques after we have a quick briefing of these dependence techniques. The first one we will have a look at is the multiple regression. Now, in the example that I spoke to you about, suppose previous research has established that cars with higher engine capacity and higher unladen weight offer lesser fuel efficiency. This was probably established by some tests done earlier, and if a researcher wants to predict currently the fuel efficiency based on engine capacity and the unladen weight, then fuel efficiency is a dependent variable, while engine capacity and the unladen weight are the independent variables. The researcher then collects data on fuel efficiency, engine capacity and unladen weight of about 100 plus cars, using the same type of fuel of course, and would possibly use the multiple regression method to predict fuel efficiency. Now, we must remember that in order to use a multiple regression method, the dependent variable and the independent variable must all be metric data. We have a look at the multiple discriminant analysis. If our dependent variable is dichotomous, or in other words, it is a categorical variable or a nominal variable, it is non-metric, then MR or the multiple regression would not be an appropriate technique, but multiple discriminant analysis, the MDA, would be an appropriate technique. The independent variables in the MDA still need to be metric data. MDA helps to understand the group differences and to predict the possibility that an observation or the object would definitely belong to a specific group. Now, while we discussed earlier about the fuel efficiency of the car being dependent upon the unladen weight and the engine capacity, if we are going to classify the cars into big cars and small cars, it's actually dichotomous, small cars and big cars, two groups. So, the dependent variable is now no more a metric variable like fuel efficiency, but it is about whether it is classified as a big car and a small car depending upon the unladen weight of the car and the engine capacity. And if we have the data on about 100 cars, then we can use the multiple discriminant analysis in order to see whether the car belongs to the category of a big car or a small car. So, here comes MDA if we have the dependent variable as an non-metric variable. The Logit regression, which is also known as a logistic regression, is a combination of multiple regression and multiple discriminant analysis. Although the regression principle is similar to that of the one in MR, the multiple regression, the dependent variable in a Logit regression need not be metric, just as in the case of the MDA. Another distinguishing fact of the logistic regression is that it can accommodate both metric and non-metric independent variables and overlooks the multivariate normality assumption. Okay, now if we have a group of variables for the dependent variables and for the independent variables, now it's going to be a little more complex, and the ideal tool here would be the canonical correlation analysis. So if there are multiple metric dependent and metric independent variables to be correlated and regressed, then canonical correlation analysis is the best tool, because in multiple regression you had only one dependent variable, whereas canonical correlation analysis allows us to actually determine the associations between two sets of variables. We might study the relationship between a number of indices of fuel efficiency, the dependent variables such as the indicated horsepower, the brake horsepower, and the independent variables such as the engine capacity, unladen weight of the car, and the age of the car. So if we have sets of independent variables and sets of independent variables, groups or sets of independent and dependent variables, the ideal one would be the canonical correlation analysis. Now we come to the MANOVA or MANCOVA, which we call as multivariate analysis of variance and covariance. Now this is done in order to simultaneously explore the relationship between multiple categorical independent variables, which are also called treatments, and two or more metric independent variables. An ideal technique would be the multivariate analysis of variance and covariance. If the analysis requires the elimination of the effect of the uncontrolled metric independent variables, which we call as covariates, on the dependent variables, then the multivariate analysis of covariance, MANCOVA, is used. Both MANOVA and MANCOVA may be done as one way or as factorials. In our car example, with fuel efficiency as a dependent variable, age of the car can be treated as a covariate. In other words, we would like to suppress this effect when we are trying to do our analysis. Conjoint analysis is another contemporary dependence technique that would help us to determine or evaluate the importance of attributes in different levels. Now, in experimental design and engineering, we have a parallel to what we do in conjoint analysis and management decision making. Here in conjoint analysis, let's say for example, we have three attributes of the car, wherein we have airbags, the speakers in the car for infotainment, and the steering wheel height adjustment. Let's say these are three attributes which are going to be offered in three different levels. For example, airbags can be offered as 2, 4 or 6 airbags. Speakers could be 2, 4 or 6 speakers, and the steering wheel adjustment in the car could be either low, medium or high. Now, three attributes: airbags, speakers and steering wheel adjustment. Each of them have three levels: 2, 4, 6 airbags, 2, 4, 6 speakers, and low, medium and high in steering wheel adjustment. Now, if you want to know the popular combinations preferred by the car owners or car enthusiasts, we could probably ask them, do they prefer 2 airbags and 4 speakers along with a medium level of steering height adjustment or steering wheel adjustment, or they would like 6 airbags and 2 speakers, or a high level of steering wheel adjustment. There could be multiple combinations, and it could make up to 27 combinations. If somebody is interested in the product design of the car, he might want to know, based upon customer feedback or a driver's feedback, which combinations are the best ones to offer, which will move well in the market. Then he will have to probably ask them to rate all 27 combinations before deciding upon which ones are the most preferred. But in conjoint analysis, without testing out all the 27 combinations, we can bring down the possible combinations to just 9 or more, and then out of them we would be able to identify which are the best possible combinations to be offered. So conjoint analysis actually helps us to bring down the combinations if they are multiple levels and multiple attributes. This small example is just about 3 attributes and 3 levels, which yielded 27 combinations. How much more with multiple factors in a product like a car? So conjoint analysis actually helps us to see which combinations are best and how we are able to identify the best ones among them. Now we come into the structural equation modeling, a very popular technique among researchers here, with multiple regression examining only a single relationship between the dependent variable and multiple independent variables. In the structural equation modeling, it's possible for us to examine multiple relationships simultaneously, and in general a confirmatory factor analysis is done prior to the structural equation model. The structural equation modeling, which we will probably call as SEM, consists of the structural and the measurement model. The structural model may have one or more dependent variables and one or more independent variables with all these relationships defined. Each of the dependent variables and the independent variables may either be uni or multidimensional, and each of the dimensions may be measured using scale items for indicators. The confirmatory factor analysis will actually show the contribution of each scale item to its dimension and the extent to which it measures that particular dimension. By this measurement model, we have evaluated the power of the contribution of the indicators to each of these variables. After the validity and the reliability of the measurement model has been established, the structural model is evaluated to establish and prove or to disprove the hypothesis that we have framed based upon our theory. So structural equation modeling actually supports simultaneous assessing of relationships and accommodates multi-item scales. Now we have just completed with the dependence techniques, and now we are looking at the interdependence techniques. Unlike in the dependence techniques where we had a very specific dependent variable, in the interdependence techniques we don't have a single or multiple dependence variable, but we find that all the variables are interdependent on each other. So probably the name interdependence techniques, and 4 very popular interdependence techniques are the factor analysis, the cluster analysis, perceptual mapping, and the correspondence analysis. Now factor analysis, which we would classify as exploratory and confirmatory factor analysis. In the exploratory factor analysis, the predominant aim is to reduce the number of measured variables into meaningful factors or variates where we don't lose much information. This can be done either by the principal component method or by common factor analysis. Suppose we have this case of a prospective car buyer considering the color of the car, the aerodynamic design, the body colored bumpers, height adjustable steering column, driver seat height adjustment, touchscreen for infotainment, the anti-braking system, the ABS, and the airbags. So we have about I think 1, 2, 3, 4, 8 here, 8 attributes here. Now if we have asked the car buyer to rate these factors or variables on a 7-point rating scale, and then we would like to group these 8 variables into smaller sectors or segments into 3 groups. Now let's say I group color of the car, the aerodynamic design, and the body colored bumpers as the external features, and the internal features include height adjustable steering column, driver seat adjustment, touchscreen for infotainment, and the safety features are ones which have the ABS and the airbags. Now, although I had named these 3 as external factors, the internal features and the safety features, there would have been an underlying structure which was identified by the software while the factor analysis was run, and this underlying structure was based upon the ratings given by the prospective car users. Now this underlying structure ratings is the one that grouped these factors, which we probably named these 8 of them into three factors, which are external features, the internal features, and the safety features. So essentially, factor analysis helps us to reduce the number of the measured variables into meaningful factors, but with very little loss of information. Now, we move to cluster analysis. In the car example that we have been speaking of, suppose we had data on engine capacities of about 130 cars. The engine capacities could have probably ranged from about 799 cc to 2399 cc, that's typically about 800 to 2400 cc. And if we want these 130 cars to be placed in three groups, namely small, medium and large cars, cluster analysis would be a very recommended technique. The cluster analysis algorithm actually places these objects in homogeneous groups depending on the characteristics specified by the researcher. In this example, these cars would be placed in the groups based on the engine capacity. Clustering can be done based on multiple characteristics too, more than one characteristic at a time. We can either follow the hierarchical or the non-hierarchical clustering procedures. Basically, hierarchical methods could be either agglomerative or they could be divisive. The algorithms followed in the hierarchical methods are single, complete and average linkage methods. The other methods are the centroid and the wards methods. Alternatively, the non-hierarchical clustering algorithm popularly follows the k-means algorithm and places the objects in cluster groups once the number of clusters are specified. The decision on whether to adopt the hierarchical or non-hierarchical procedure depends upon the choice of the researcher and the problem that we have designed. Now, another very popular technique is the perceptual mapping. If we consider two dimensions of the car, namely fuel efficiency and driving comfort, and we would like to know how much the brands of cars currently available in the market are positioned in the minds of car enthusiasts and perceived by the car enthusiasts, then an ideal technique would be the perceptual mapping, which is also known as a multidimensional scaling. We would be positioning the brands of these cars on a dimensional scale, and depending upon whether it is more towards fuel efficiency or it is more towards driving comfort as perceived by the respondent, we would know where the brand or the variate of a particular car is positioned. The MDS or the perceptual map typically helps a researcher to determine the perceived relative image, a relative image of the cars considering the two dimensions. In MDS, unlike in factor or cluster analysis, a solution can be obtained for each respondent and there is no variate here. The researcher makes choices between similarity and preference data, disaggregate and aggregate analysis, and on whether to use the compositional or decompositional methods. Although earlier MDS programs were predominantly non-metric in output, the contemporary programs of today provide metric outputs. Now, correspondence analysis is the next technique. If we have non-metric data such as color of the cars, classification of car size such as small, medium and large, and we want to position the cars in a perceptual map, then the technique to adopt is the correspondence analysis. Here it actually starts with the cross tabulation of the two attributes, namely colors and the size of the car. Then it does a non-metric to metric conversion, then does the dimension reduction, and finally the perceptual map is prepared. So correspondence analysis is the best option for a multivariate representation of interdependence for non-metric data. Now the next screen actually shows us the nature of the data, the dependent variables and the independent variables. For the list of the dependence techniques, we have the canonical correlation, MANOVA, ANOVA, MDA, multiple regression, conjoint and the SEM listed here. Now we find for the canonical correlation, the dependent variable can be metric or non-metric, and the independent variable can also be metric or non-metric. But in the MANOVA, the dependent variable needs to be metric, the independent variable can be non-metric. In the ANOVA, the dependent variable needs to be metric, the independent variable can be non-metric. The MDA, the dependent variable can be non-metric, the independent variable needs to be metric. In the multiple regression, the dependent variable needs to be metric and the independent variable can be either metric or non-metric. For the conjoint analysis, the dependent variable needs to be non-metric and it could also be metric, but the independent variables are non-metric. And the structural equation modeling, the dependent variable is metric, the independent variables could be metric or non-metric. So, having seen the nature of the data that we require for each of these dependence techniques, we are just about to close with some generic tips to perform the multivariate analysis. We have 6 points listed here. We need to ensure that both statistical and practical significance exist in the research that is being carried out. The sample size should be just adequate, not too big, not too small. We need to understand the nature of the data well to choose the right kind of technique, and just the right amount of variables need to be used. For example, parsimony, a significant characteristic in research, should be followed. Just the right amount of variables, or the minimum amount of variables, or probably the optimal amount of variables in the model should be used to obtain the desired results. And then we need to identify and eliminate the errors, and we also need to ensure a foolproof validation of the results. So, the choice of multivariate techniques that we need to use, essentially, as I started in the beginning of the slide, needs to be based upon the nature of the problem and the nature of the data. So, a problem well defined is half done, and then data well collected carries us through to the next 25% of our research, and then finally the last part is about the analysis and the interpretation, and the right choice of tools would again, as I emphasized, would be based upon the nature of the research question and the nature of the data, and the right tools used on the right data would answer the research question right. So, I guess this would have given you a fair overview of the possible available multivariate techniques, and I repeat, these are not all that are available, these are not just the exhaustive ones, but these are some of the most popular ones, and this must have given you a little bit of a curiosity to read through them a little more. For further reading, may I recommend the books by Barbara and Linda and the books by Hare et al. This would help you understand these techniques a lot more in detail and would also help you to do these analyses well. So, I close here. Thank you very much and bye-bye.